In the previous video in this series, you learned how to create temperature reports, select object faces, and make cut plane animations to show temperature maps for natural convection and still air. In this video, you'll see the difference that forced airflow makes on the temperature. You'll learn how to perform post-processing in IcePack after specifying forced convection as the thermal simulation type in SI-Wave. In SI-Wave, under the Simulation tab, select IcePack. Input a setup name. On the Thermal Environment tab, verify that the forced convection type is active. Accept the default values for the setup. Air will flow across the board in the plus X direction, from left to right, at a speed of 2 meters per second. The power dissipation values for the different objects on the PCB are the same as the still air simulation. On the IcePack cabinet size, accept the default values for the padding. Launch the simulation. In SI-Wave, you can display these temperatures on various layers and elevations. Click the Temperature Plot Visibility control. Step through the different elevations for the layers to see the hotspots. As you might expect, there are temperature increases around the active devices, and particularly the voltage regulators. Now open the project in IcePack for a more detailed analysis. Go to Results and select IcePack Sim 2. In IcePack, select the Power and Temperature Limits option. Define the temperature limits for the different objects. Go to Post and click Power and Temperature Values. Observe that the temperatures are well within the operating limits. To see what happens when temperatures are beyond their operating limits, define an artificially low temperature limit and compare the values against it. Click All to Default to update the temperature limits. Click the Show Too Hot button. Components above the temperature limit are shown in red. You can try different default values. Click the Show Marginal button. Any component that is within 5% of the temperature limit will be displayed in yellow. Click Unset All and then revert to the initial settings. Select all the objects using the Shift and Control keys. Leave out the heat sinks for now so that you can clearly see the IC temperatures. Right-click and select Create Object Faces Combined. Faces are generated for all the selected objects, and the temperature map and scale are displayed. Notice the substantial drop in temperature. The peak value was in the 50 degrees C range with still air. Now it is just in the 30s. You can also include the heat sinks in the plot. Click Accept and click Update. The temperature map can be viewed using the scale as reference to see the different temperature ranges across the PCB. Fit the model to scale. Right-click Face 1 and hide contour. You'll now create a cut plane and generate contour plots, vectors, and particle traces. Click Plane Cut. Select the Show Contours checkbox. Set the position using the coefficients of the plane. Select the Loop Mode checkbox. Click the Parameters button and accept the default. Click Apply to create the contour on the cut plane. Now animate the cut plane. These plots show that the heat is being transported downstream by the airflow, away from the hottest components. Press H to see the top-down view. At any point, you can interrupt the animation to manipulate the settings or the position of the model. Deselect Show Contours. Click Update. Select Show Vectors. Click the Parameters button. Select 3D for the arrow style. Change the max pixels to make them smaller or bigger in size. In this case, increase it to 75. Leave color by velocity magnitude. Click Done. Click Animate to see the vector plot. In these vector plots, arrows shown in orange or red correspond to the fastest airflows. Next, you'll create a particle trace plot as an alternative way to visualize the airflow around the board. Stop the animation of the vector plot. Deselect Show Vectors and Update. Click Done. For particle traces, create a new object face list using the inlet object. This will show the streamlines as the flow enters and leaves the domain. Under Cabinet, right-click Inlet and go to Create Object Faces Combined. Deselect Show Contours and click Update. Click Show Particle Traces and Parameters. Set Speed as the color variable. Click Apply. You'll have to manipulate the settings to get traces of appropriate size and dimensions. So set Uniform to 75 and Trail Width to 2. Click Apply. Decrease the trail width and increase the size. Click Apply. These particle trace plots give you insights into where the airflow may be obstructed and less effective at cooling the board. Now that the particle trace plot looks good, rotate the model and press H to see the top-down view. This concludes this video series on how to perform electrical and thermal co-analysis of a printed circuit board using ANSYS SI Wave coupled with ANSYS IcePack.